second half of Module 13 is about a concept called regression. Now, the Pearson correlation measures a linear relationship between two variables. You remember that if you have a variable on the x-axis and a variable on the y-axis, then you can plot each person's placement on both variables at the same time. If you kind of draw a circle around that shape, that is an estimate of how wide that circle is, how spread out the scores are. That's an estimate, a visual way of estimating how big the R is. So dots that are very closely clustered together, it's going to be close to 1. And dots that are far apart, it's going to be further away from 1, closer to 0. But if you draw a line through the data like this, that makes the relationship yet easier to see. It also shows the central tendency of the relationship and can be used for prediction. So when I say it shows the central tendency of the relationship, what I mean is just like the mean of a set of scores shows the center of the distribution by one definition, the line of a correlation or a scatter plot of data points shows the middle, the center of that set of scores. So it shows the central tendency, where the scores tend toward the center. What's the middle of the scores? And as I said, it can be used for prediction. Now, we have an individual who got like 619 on their SAT scores and a GPA of like 3.26 during their first year of college. This individual point right there reflects a person who got that set of SAT scores and GPA scores. But we don't know what somebody would get in their first year of college on their GPA if they had an SAT score of say 600, okay? If we just follow this up, we don't have a dot to estimate what a person would get in their GPA if they got exactly 600 on the SAT. But if we draw a line through the center of the relationship, then we're able to say we predict that somebody would get a GPA of about 2.75 if they got an SAT of about 600. So that allows us to make a prediction about one variable based on a value of another variable. So a regression analysis precisely defines the line that we draw. Now you could just eyeball it and draw a line through the center of relationship, but if you want to know exactly where the line ought to be in order to show the center of the center of the relationship, then you have to perform a regression analysis, and that's what this part of the module is about. Now we can represent that line with an equation which follows a general form of y equals bx plus a, where x and y are the variables here, and a and b are fixed constants. Now, when you were in junior high or high school, you probably took an algebra class in which you learned the form of a line is y equals mx plus b. We're using different letters here, but the principle is the same. When you learned that form, you realized that the slope and the intercept of the line were represented within this equation. Let me illustrate what I'm talking about. Let's give an example. A video store charges an annual membership fee of $5, which allows you to rent videos and games for just $2 each. The total cost for 1 year can be computed using the linear equation y equals 2x plus 5. Because you would multiply the number of videos you rent each year times 2. And no matter how many videos you rent in the year, you would have to add 5 for the membership fee. So if you rented 0 videos, then you would still pay $5 because you would have 2 times 0 is 0 plus the $5 base fee. That would be if you rented none, you would pay $5. If you rented 1 video, then you would pay 2 times 1 is 2, plus 5 is 7. So you'd pay $7 for the year. So Y represents how much you pay per year. X represents how many videos you rent. Now, if we plot these two variables in a graph, you could have the number of videos that you rent as the x-axis and the total cost per year as the y-axis. Now, if we imagine to ourselves that we're renting 3 videos a year, then we can plug in 3 for the x variable here and plug in the constants, $2 per video, $5 per membership, and we would figure out that you would pay $11 per year if you rent 3 videos. If you rent 8 videos, then you could plug in that 8 instead for the x, and you could carry the formula through, and you would realize that you pay $21 a year. In this situation, we would plot 3 videos per year and $11 paid, or 8 videos per year and $21 paid, and we would plot these those two dots right there. That would allow us to connect the dots and draw a line that represents the regression equation that we computed over here based on the scenario. Now, B in the equation is the slope of the line. The slope is the amount that y increases each time x increases 1 unit. So if we rent 1 additional video, then our line increases $2. Or, as you can see here, if we go from 3 videos to 4 videos, then the amount we're paying increases from $11 to $13. It's $2 more. For each incremental unit of increase on the x-axis, we would increase 2 units on the y-axis. So when we'd go from 3 to 4, it goes to 13. 4 to 5, it goes to 15. 5 to 6, it goes to 17. So B right here represents the slope of the line, how much it increases in y for every value of x. The A is the intercept. This is where the line crosses the y-axis. So if you have 0 videos you rent in a year, then you still have to pay that $5 membership fee, and that's where the line crosses the y-axis. So it represents how much of whatever your dependent variable is, you will find if there is none of your independent variable, if the value is 0. Now, regression is a method of finding an equation that describes the best fitting line for a set of data. But one might ask, how do we define a best fitting straight line when there are so many possible straight lines? So in this set of data, unlike the last, where we had a fixed formula to determine how much somebody would pay, the relationship between height and self-esteem is not fixed. It's likely impacted by other kinds of variables. And so, you won't find that every dot falls exactly on a fixed line. So here, we might try to draw a line through this set of data, and it might look like this. But you could also draw this, or this, or this. How do you know which of those lines that all look like they're approximately representing the relationship between these two variables? How do you know which one's the best fitting line, the right line? Well, we define the answer to that as the line that minimizes prediction errors. Now, what does that mean? It means that if you predict how much self-esteem somebody will have from their height, or we could say how much of any DV from any IV, then we would minimize the prediction errors. That means each of these dots would be as close to the line as possible. In order to compute that, we have to introduce a new concept. This right here, this symbol, this Y with a hat on the top, is pronounced Y hat. This is the value of Y predicted by the regression equation for each value of X. The error of prediction is the difference between what somebody actually got on their Y variable minus what we thought they would get, the amount we predicted they should have gotten. Let's illustrate that here in the graph. If we have x values and y values, each of these dots represents a combination of scores that people got on both of these variables together. So this dot right here represents a person whose value on x was right here, and their value on y was right here. Now, because we drew the line right here, we would have predicted that this person right here, if they got this x value, should actually have a y that was right here. This is the y we would predict. Let me show you on this example right here. If this data point right here is represented by x and y, this is the actual value that somebody got on x and on y. But they're not exactly on the line. The distance between what we thought they would get here and what they actually got here is the distance between y and y hat. The distance between what they actually got and what we predicted they would get. Because remember, y hat is actually the result of the formula. When we have bx plus a, which is the formula for this line, the result of that y is what we predict they should have received on that dependent variable. So the distance between y hat and y is your error of prediction, the error of prediction. So that's how far off our prediction is. That's how much error there is in our prediction. The regression procedure produces a line that minimizes total squared error of prediction, because some of the raw errors are positive and some are negative. So if you add up all of the negative errors that fall below the line, like this, and all the positive errors that fall above the line, like this, they will add up to 0 if you have found the actual regression equation that best represents these two variables. Now, as we saw in early modules, if you're trying to compute something based on a set of values, if you're trying to compute the standard deviation from a set of values, the standard deviation is computed by squaring the deviation scores, because if you just take the average deviation, it's always 0, and that's not a very good representation of how much the scores actually differ. If you computed the average deviation, you just add them up and divide by how many there are, it will always equal 0, and that would suggest that there really are no differences. The average difference is nothing between any given score and the mean of that set. So in order to get around that, we have to first blow them up and then shrink them back down by squaring all the deviation scores, figuring out the average, and then shrinking it back down by taking the square root of it. We do the same thing in the regression equation, where we square all of, where am I? The total squared errors of prediction. We square all of these errors of prediction to see how far these dots are from the line. And then we, at the end when we're finished, we shrink them back down by taking the square root of them. So this method is called the least squared error solution. It's the method that results in the least squared error between the prediction that we have and the actual data points that we have. Now, as I said before, the regression equation for computing a variable is y hat equals bx plus a. This equation gives the line that would best predict y for each value of x. And in order to figure out what that b and a should be, we have a formula. The b is calculated as the sum of products divided by the sum of squares for x only, just that variable. And the intercept can be found as the mean of the y variable minus b, which you just computed, times the mean of the x variable. So let's go through an example to see how b and a are calculated and placed into that formula that's y hat equals bx plus a. So we have these two variables here, x and y. We have a set of scores on each of those variables. Remember, the first person got both of these scores. They got 5 on the x variable and 10 on the y variable. Now, if we compute the sum of the x scores here, if you add them all up, it's 32. And if you divide by how many there are, there's 8 here. So 32 divided by 8 is 4. And if you add up all the y variables, the sum of y is 56. And if you divide that by 8, it's 7. Now, when we computed our correlation before, we took an x minus the mean and a y minus the mean of y. So here's our x variables. We take 5 minus 4 is 1. 1 minus 4 is negative 3. 4 minus 4 is 0. 7 minus 4 is 3, etc. Here we take y minus the mean of y. Here we've got 10 minus 7 is 3. 4 minus 7 is negative 3. 5 minus 7 is negative 2, etc. Once we've computed those deviations, then we can square them. We square each deviation, and that allows us to compute the sum of squared for the x variables. And if we do the same thing for y, if we square these deviation scores for y, we compute the sum of squares for y. We've been doing this for a very, very, very long time, so we understand that. But the sum of products, as you remember, is to multiply the deviation scores of x and the deviation scores of y. So here you take these deviation scores and multiply each one by these deviation scores. So 1 times 3 is 3. Negative 3 times negative 3 is 9. 0 times negative 2 is 0. 3 times 4 is 12, etc. If you sum those up, that's the sum of products. We call it the sum of products, as you recall, because we're multiplying together both of the deviation scores. The result of that is a product. Okay, so we're multiplying them together. We call that a product. If we add up all these products, the sum of products is 56. Given this stuff that we already know how to compute because we did it, well, we've done this for modules and modules and modules now, but because we did this earlier in module 13, we now can compute B and A. The sum of products, 56, goes here, and the sum of squares for x is 28, that goes here. If you carry that through, it equals 2. The mean of y is found here, 7. The mean of x is found here at 4. And if you take 7 minus b, 2, times 4, then you have 7 minus 8, or negative 1. Now, we should be able to put this into a regression equation. What will that be? Y hat equals 2x minus 1. bx plus a. So 2x minus 1. How would we interpret the slope here? Hopefully you remember that the slope is how much of an increase we find in y for each 1 unit increase in x. So if x increases by 1 unit, then y increases by 2 units in this example. Whatever value we have here, that's how much y will increase every time x increases by 1 unit. How do we interpret the intercept? This is where the line will cross the y-axis. So in this situation, it will cross at negative 1. You could also say that this is the value we will have in our dependent variable if there is no x. If we have 0 units of x, then we will expect to find negative 1 in our dependent variable. Now, this is the set of data that we just showed on the last screen, and this is the line that we just computed. Y hat equals 2x minus 1. So we draw this line right here, and you can see that the regression line passes through the point that's defined by the mean for x and the mean for y. So you remember on the last slide that the mean for x was 4 and the mean of y was 7, and if you draw a dotted line here that crosses the mean of y and the mean of x, the line that's the regression crosses through both of those points. You should also notice that the sign of the correlation is the same as the sign of the regression's slope. So in this situation, there's a positive correlation because the data are sloping upwards towards the right. If you look at the slope, it's a positive value, positive 2. If there's no correlation, then the slope will be 0. So if you have scattered dots that are all over and the best fitting line is flat, then that would mean there's no slope. It's 0. And if you had a negative slope, if this were negative 2, then the line would be going down 2. For every increase in x, you would find that y decreases by 2 units, if this were negative. Now, we can use our regression equation to predict things. If you know someone has an x score of 3, what would be predicted for their value of y? So in this same situation that we just computed, if you look at where the 3 is, you would expect that they should get something about 5 for their value of y. Why is that? Because if you plug in 3 right here in the x, 3 times 2 is 6, minus 1 is 5. Now, as you can see here, we actually have an individual who got a 3 on x and a 5 on y. But we often don't have an individual who gets the exact score that we predict for them on the x. And even if we do, like if we have an individual who got a 4 here and we were trying to predict what they should get if they were a 4, it doesn't mean that their y variable will actually be exactly what the regression equation predicts, because the regression in this case would predict you should get a 7, but this person actually got a 6 and this person got a 5. When we interpret prediction values, we have to use caution about a couple of things. As I just indicated, the predicted value is not perfect. How far off your predicted y is from the actual y is related to the correlation coefficient. So you recall that the correlation coefficient, R, represents the strength of the relationship, how tightly clustered the dots are to each other. If the dots are very tightly clustered, then you will have very little error. Most of your dots will be very close to the line. But if you have a wide R, a wide spread of scores and a smaller R to represent that those scores aren't very tightly clustered, then you will find that there's a lot more error in prediction, that your dots are spread further out from the line. And so you would see that each individual dot has a lot more error associated with it. Another caution is that you should not use the prediction equation to make predictions for x values that fall outside the original range of values that you used to form your prediction equation. You recall that when we were doing the first part of Module 13, we talked about correlations, and how if you had like an IQ that was a restricted range between like 110 and 130, then the creativity among those people would not be a widespread range of creativity. But if you increase your spread of IQ, then you see that in fact there is a correlation between creativity and IQ. Just like that, in this situation, if we have a restricted range of values, we don't know what will happen if we keep measuring x's that are larger than this. Will the relationship continue to be straight and linear like this, Or will it become a asymptote where it kind of tapers off? Or will it become a U-shaped relationship where it will actually dip back down? Because we don't know what will happen, we have to only predict what somebody will get in their y within the range of the dots that we have on our x-axis. So here we have dots that range from about 1 to about 7, and we should not use our prediction equation to predict very much beyond that. We might use it to predict a little bit lower or a little bit higher, but not much. Now, as I said earlier, the amount of error in your line will depend on how strong your correlation is. Regression equation makes a prediction, but there's usually some error in the prediction. In this situation, there's no error. There's a perfect correlation of r equals 1. And so every every dot falls exactly on the line. In this situation, there's a strong correlation, but it's not perfect. There's some error in the dots, meaning that not every dot falls on the line, and so for this dot there's some degree of error, for this dot there's some degree of error, for this dot there's some degree of error, for this dot there's really no error, but for all the other dots there's some distance between where the dot falls on the y-axis and where the line is predicting that dot should fall on the y-axis. So the precision of the estimate is measured by an equation that we call the standard error of estimate, SEOE, standard error of estimate. This gives a measure of the standard distance between the predicted values on the regression line and the actual y values that exist in the data. So this is the concept that I've been articulating many times before, where the y actually falls versus where the y was predicted to fall. That distance right there is computed, the average distance is computed by the standard error of estimate. So that is the sum of squares residual divided by the degrees of freedom. What is that? You take the square root of that. Why is it square root of SS over DF? Because, as you recall, the standard error of estimate is calculated very similarly to the standard deviation, the square root of the variance, the square root of SS over DF. Now, in this situation, we have to do something slightly different than we do with the standard deviation because this is two variables we're dealing with, not just one, right? But still the concept is very similar. What we're trying to figure out here is what's the average distance, the typical distance of any given score from the mean predicted value. But in this situation, instead of having a flat mean, we have a line mean. The line represents, this diagonal line right here represents not the arithmetic mean, but the average of what we predict on this y variable given what we know about their x. So we're still trying to figure out how far away is each of these points from the average of the set of scores. In order to do that, we have to compute the distance between each individual actual score on the y variable minus what we predict they should have gotten. So y hat, and that distance for every score is squared, and you add them up, and that's the sum of squares residual. Residual is a word we use in statistics to mean error, or how far off we are in our predictions. It's how much we haven't accounted for. It's the leftover variability that we haven't accounted for. So that's why we call it residual, because it's leftover. So this right here is the amount of variability that's left over that we haven't accounted for. It's how far off our estimates are, divided by n minus 2, because as we learned in the last part of the module, the degrees of freedom for correlation and regression is n minus 2, because a straight line always needs 2 dots before it can be drawn, before a line can be drawn. After that, it's free to vary. There's more there's more possibilities for drawing a line. But if you have 2 dots, then that line will always be fixed. There's no possible variability. There's no degrees of freedom. So the degrees of freedom is everything that's left over after we take away the first 2 dots. All right. Let's walk through an example of calculating the standard error of estimate. Let's use the same data that we did in our last example, where we already calculated the scores for x and y, and we figured out all the sum of squares and sum of products and all of that stuff. Well, here we need to use our regression equation that we computed, which was y hat equals 2x minus 1. And we need to use this equation to figure out what do we predict somebody should get on y given what they actually had on x. So we take this x value of 5 and we plug it into the equation and we say 2 times 5 minus 1 is 9. Now they actually got 10, but we think they should have gotten 9 if they were following the regression line perfectly. Then we do the same thing in this situation. We take the 1, we put it in the equation. 2 times 1 is 2, minus 1 is 1. We predict they should have gotten 1. They actually got 4, but we think they should have gotten about 1. Then we take the 4 and we plug it in. We do the same. We carry these all through. We figure out what they should have gotten on y for every variable, and we compare that to what they actually got on y. So here the residual, what we haven't accounted for, the leftover, the error, that is y, what they actually got, minus y hat, what we thought they should have gotten. So 10 minus 9 is 1. 4 minus 1 is 3. 5 minus 7, negative 2, etc. So we figured out what the difference is between what they actually got and what we thought they should have gotten, and then we square the residuals so that we can get rid of these negatives. If you just add them up and take the average of these right now, it will be 0. And that's disingenuous. You can't say the average distance of all of these dots from the line is 0 because they didn't all actually fall on the line. So a better way of getting at this is to square them first, then take the average, then square root it to undo the squaring process, just like we did with the standard deviation. So here, if you square them, each one of these, 1 squared is 1, 3 squared is 9, negative 2 squared is 4, etc. And then you add them up, then you get the sum of squares residual. That's the sum of squares that's unaccounted for, that's error, how far off our prediction is, how much variability there is because we're off. And that comes to 44. So that's our error variability. We take that, we plug it into the equation, we divide by the square root, we divide by n minus 2, which is in this case 8 minus 2, 6. And if we take the square root of that, then we get 2.708. That's the standard error of estimate. But how can we interpret this value? Take a moment, pause your video, and see if you can figure out how do you interpret this value. Just as we did with the standard deviation, when we were interpreting that value, we would say if the standard deviation was like 1.5, what we were saying was the typical distance that any given score in our sample, how far it was away from the mean, was about 1.5. Sometimes it was more, sometimes it was less, but it was usually about 1.5 points away from the mean. In this situation, what we're saying is, with a value of 2.7, we can say 2.7 units is how far away the dots in that scatter plot typically fall away from the line. So if I go back for just a second, you'll see that in this situation, each of these dots is about 2.7 units away from the line, either higher or lower. Some of them are further away than that. Some of them are closer than that. But on average, typically, they're about 2.7 units away from the line. So here, the line is at about 1. And if we look at where the dot actually is, it's at 4. That's 3 units away. That's about 2.7. This is at 0, but we think it should be about 3. Look, it's almost exactly 3 points away. We estimated it should be about 2.7 away. This one's closer. There's no error here. There's no distance between where the dot is and where it should be. So the error there is 0. Here, it's 1 distance away. Here, it's 2 distances away. Here, it's 1 distance away. Here, it's looks like maybe 5 distances away. But the point is, on average, it's about 2.7 units away from the line. That's how we interpret this value. Now, there's an alternate method for calculating your standard error of estimate. You have this in your formula sheet, and you're welcome to rely on this formula if you want. I'm going to explain very briefly why it works, but it's less conceptual in my mind than the other, and so I wouldn't try really hard to understand it this way. But if you're in for a ride, here we go. As R increases from 0 to 1, remember R is the correlation, and 0 represents no correlation, and 1 is a perfect correlation. As R goes from 0 to 1, the standard error of estimate decreases down to 0, meaning if you have a perfect correlation, you have no error. There's no typical error in that situation. But if you have something slightly less than 1, then your standard error of estimate will be a little higher than 0. If it's very close to 0, if your R is very close to 0, then your standard error will be very large. There will be a lot of error. Now, since R squared is a percentage of variance in the y-scores that's accounted for by the regression equation, remember we've been talking about R squared as a percent of variability accounted for lots and lots of modules now. But because it's a percentage of variance that's accounted for by the regression equation, the sum of squares for the regression, that's the variability in the regression, is equal to the percentage of variability accounted for times the sum of squares that exists in that variable. So the variability in that variable. So when we say SS regression, what we're saying is how much of the variability we've accounted for is the total amount of variability times a percentage of variability accounted for in our model. That means that the rest of the variability in that variable y, in other words, the unpredicted portion, is the inverse. It's 1 minus R squared times sum of squares y. So the sum of squares residual, the stuff we didn't account for, the error, the leftover residual variability, is everything else that's not R squared. So you can imagine in a given situation, if you have R squared is 72%, this is the variability that you've accounted for. All the variability that you haven't accounted for that's left over, that's residual, is the inverse. It's the rest of the 100%. So 72, if you take 1 minus 72%, then 28% is the leftover. It's the residual. It's the rest. So 1 minus R squared is everything that's left over. And we can multiply that by the sum of squares y. And we understand then that that's the amount of variability that's left over and not accounted for. Therefore, an alternate method to calculate the standard error of estimate is based on R. So if you take the inverse of R squared, it's the variability we haven't accounted for, and you multiply it by the total variability here, SSY, then you can figure out the sum of squares residual, which this is the exact same formula as we saw on the last slide conceptually, but we're just figuring out a different way of getting to sum of squares residual. So this is the inverse of R squared times the variability in y to get how much is the error that we haven't accounted for here on the top, divided by the degrees of freedom. Take the square root of that. That's your standard error of estimate. This method is often easier to compute because R is easier to calculate than going through every single point in your data set and trying to run it through the equation to figure out what is y minus y hat and then squaring it. So you'd have to run every single value through your equation to get out the prediction value, and then you'd have to compare the difference between what it actually was and what we thought it'd be, and then we'd have to square it. And so sometimes R is easier to compute, and you can use this this formula, and it gets you the same answer, but it gets you a little faster and easier. Let's walk through an example using the second method for computing standard error of estimate. Remember, we've already gone through all of this. We already understand what all of these scores are. This is the same set of data that we had before. But in this situation, we have already computed the R. If you recall back from the first part of Module 13, we computed the R using SP and SSX, SSY. And if you carry all that through, you get an R of 0.847. You can compute the sum of squares residual, the error, how much you haven't accounted for, by taking the inverse of your R squared and multiplying that by your SSY. So if you take the R squared, it's 0.847 squared. 1 minus that is the inverse. Your SSY is 156. And if you carry this formula through, you get 43.99. That's your sum of squares residual, how much you haven't accounted for. And your standard error of estimate then can take this value, put it on the top of your equation, divide it by 6, and take the square root of that for the same 2.708 that we found before, which is interpreted as the value of how far each point is away from the line on average. They should be typically about 2.7 units away from the line. Now, what we've covered in this module is called simple linear regression. You can actually try to predict dependent variable values with multiple independent variables at the same time. If you do that, it's called multiple regression. So what we've done is simple regression. Multiple regression is when you use lots of independent variables to try to predict one DV. So an example of that might be like if you measured calories eaten per week and time spent exercising per week and somebody's height and their current weight and their gender, then you could calculate a regression equation to try and predict how much weight people would typically lose each week as the outcome variable. So if you're interested in this as your outcome, you could have a slope for calories eaten and a slope for time spent exercising and a slope for height and a slope for weight and a slope for gender, and you could create a long prediction equation that has a bx of one unit and a bx of another kind of variable and a bx of another kind of variable plus your a plus the slope, or I mean to say the intercept, and you would come out with a prediction for how much you'd think somebody would lose each week. Now, we're not going to do this in this class. I just want to highlight for you the fact that this exists. If you're using multiple independent variables and trying to guess a dependent variable, then you use this other kind of statistic called multiple regression. Now, when would you use each statistic? In Module 13, we learned about both correlations and regressions. If I ask you to test whether there's a relationship between two variables, or to see how two variables are related to each other, I'm asking you to do a correlation. If I tell you instead to predict, if I use this word predict, some kind of DV from an IV, so in other words, using an independent variable to predict what somebody would get on their dependent variable, I'm telling you to create a regression equation. Or if I tell you to develop an equation, I'm telling you do a regression. These are the kinds of statements that result in a regression, and these are the kinds of statements that result in the correlation. I'm noting this because correlation and regression are very similar to each other. We've covered them both in the same module, and you'll probably be asked to do both, but if I ask you using code words like this, you need to know which type of statistic you should run. Now let's go through a practice of calculating a regression. At the end of the correlation part of this module, we ran a correlation to see if the number of books that people read are related to their GPA. And we calculated the statistics that are shown here. So we computed the sum of squares and the mean for each of these scores on the first variable, and the mean and sum of squares for the second variable. And then we also computed the sum of products, and we computed an R. Using all of this, what we already did, calculate the equation to predict a person's GPA based on the number of books they've read. Note those key words. This is what it sounds like when I ask you to do a regression. Calculate the equation to predict a person's GPA based on the number of books they've read. What GPA would you expect someone to get if they had read 6 books in the last year? Now, we actually have somebody who read 6 books, and they got a GPA of 3.0, but we might not guess they would get exactly 3.0. So, run through, in your equation, run through what somebody should get if they read 6 books, and compare it to what this person actually got. And then, once you find an estimate for this point right here, figure out how far off it's likely to be on average. So, figure out how far is a typical dot from the line in this situation. How far off are your GPA estimates given what we know about their books read? Go ahead and pause your video. And when you've worked through your practice problem here, go ahead and push play to continue and see the answers. Here are your answers. So if you wanted to compute the b part of your equation, you would use the sum of products over the sum of squares for x. You would get 0.145. The a part of your equation uses the mean of the y variable and the mean of the x variable, and the b you just computed. And if you carry that through, you get 2.3. You can use both the b and the a to form an equation. And that equation should be y hat equals 1.45 times x plus 2.3. Or you could say it in actual terms related to the question, like your predicted GPA equals 0.145 times the number of books you've read plus 2.3 as the base GPA, that even if you read 0 books, you should still get a GPA of at least 2.3. So once you know that, then you can run through an equation. You can run this value of 6 books through the equation, and if you plug in 6 right there, then you would expect somebody to get a GPA of 3.17. You would expect that estimate to typically be about 0.198 points off on average. How did we do that? Well, there's 2 methods of computing the standard error of estimate. The first way is to take the sum of y minus y hat squared, and the second way is to take 1 minus r squared times the sum of squares for y. You can see I've walked you through the prediction method right here, and I've walked you through the r squared method here. You should compare this against what you've done, but recognize that either way you get about 0.198, and if you do, that's interpreted as the average distance off that our prediction equation is when we try to guess how much somebody's GPA will be based on how many books they've read. So when we guess their GPA, we're going to be about 0.2 units, GPA units off on average. Hopefully that makes sense. If you have any questions, as always, please reach out. I'm happy to help with anything I can. Take care.